Good afternoon, and you're very welcome to the AtlanTec Festival 2022. We're back on our 8th year, and we've been running a very special event this year with multiple events over multiple virtual venues. We're in the home stretch now. We've just today and tomorrow to go. If you're on social media, you can follow us on AtlanTec Fest and use the hashtag AtlanTec. I'm Ian Gallivan. I'm the moderator for the day. I work in the commercialization function in NUI Galway. I work at the intersection between industry and academics, and it's a very unique perspective to see how research moves between the academic community and the industrial community, and how the collaborations can be affected. Our speaker today is Owen Clifford. Owen is a senior engineer in civil engineering. He's at the forefront of water research in this country, with multiple international and national academic and industrial research partners. Today's talk is about the intersection of data and the water systems and wastewater systems. And it'll deal with the challenges that are facing the water systems and the stresses and strains, and give us some indication of how some of those challenges can be met. So just before we move on to Owen, I just wanted to have a quick shout out to our sponsors. Without them, we wouldn't be here, and year after year, they step up and support the organization, support the festival, and create this ability for us to share and communicate and learn from each other. So, and with that, I'm going to hand over to Owen and let him take it from there. We'll be using the Q&A function. I'll be watching that. So please use that as an opportunity to throw the questions. Owen's well able for any questions on the topic. And I know it's going to be an interesting topic for most people because it'll affect how we lead our lives into the future. With that, I'll hand you over to Owen, and I'll see you on the far side.
And thanks very much, Ian. And also just to say that Ian has been very helpful to us over the years with a lot of the research that I will be talking about today. So I'm just going to share my screen now. Bear with me. So hopefully that's all visible. So thanks, as Ian said, I'm just a senior lecturer in civil engineering in NUI Galway, and I'm going to talk to you today about how data engineering can drive the next level of efficiency in wastewater treatment. But I'm actually going to start off with maybe a broader overview of the water sector, given maybe, I'm not sure the background of people attending here, but I think it's useful to understand a little bit about where the broader water sector is and this new concept of digital water. And then I'll move into what wastewater treatment is, where we use data in wastewater treatment, and maybe some future perspectives from that. So I think there's a kind of a simple way of summarizing the role of the water sector. So that's water, wastewater treatment, and sanitation. And I've just picked 3 graphs, and the 3 graphs list different, I suppose, types of infrastructure or services and their impact on life expectancy. So one of them is the impact of health expenditure on life expectancy. And as you'd expect, in general, there's a correlation. The more you spend on health, the longer your life expectancy in different countries, up to a certain point. If we look at access to clean water, we can again see there's very clear correlation. Areas with access to improved drinking water supplies will have higher life expectancy for any given income. And again, you can see there is some scatter in that, but there is a clear trend. And the final one then is improved access to improved sanitation and life expectancy. And this is what maybe shows the strongest trend of all 3, and in many studies shows the strongest trend of any service or infrastructure or factor that you can measure in terms of life expectancy. So what we're saying here is the thing that maybe we take for granted in Ireland, which is improved sanitation, is actually the single biggest impact in terms of life expectancy. And I think that's maybe a neat way of summarizing the importance of this sector. So where are we now with the area of water and sanitation? And unfortunately, not to paint a bleak picture, but I think given the times we're in, it's unfortunate that still over 1.5 billion people have no access to a toilet of any type, and just under half the global population have no access to safely managed sanitation. And, I think it's astonishing to think that more people have access to a mobile phone than safe sanitation. And when it comes to other areas such as schools, about a third of all global schools lack access to basic water and sanitation. And that has a huge impact on countries' economic development and child development in different countries. So we have a long way to go in the area of wastewater treatment and water supply and sanitation. Not that we haven't done a lot. Even in Ireland over the last number of years, on the top left-hand side there, you can see that there has been a significant improvement in the number of areas that are complying with the urban wastewater treatment directives in Ireland. So it has reduced. Areas that have failed have reduced from just under 30 to maybe just above 10, and that trend is going downwards. And we see in various countries around the world, particularly in China, there has been enormous improvements in access to sanitation in rural China, which has made a huge impact on quality of life. And even across Europe, there has been very significant improvements driven by the EU in the area of wastewater treatment and water treatment, albeit there are differences between different countries, particularly maybe in Eastern Europe versus Western Europe. But there is a lot more to do, even in the developed countries. In Ireland, we have a number of scenarios, situations where we have raw sewage overflows into various surface water bodies. This may be due to stormwater and also due to sewage, and also due to the capacities of sewer systems and wastewater treatment plants, albeit there is a lot being done in this area. We see across Europe, there are historical legacy issues, particularly in urban areas, with regard to raw sewage entering rivers and streams and canals. And even in London, one of the biggest infrastructural projects in the world is ongoing at the moment to, I suppose, rebuild their Victorian infrastructure systems. And we can see also the impact in developed countries on drinking water supplies, where nitrate pollution stemming from human activities and wastewater that hasn't been fully treated enters into groundwater and makes that groundwater unfit to drink. And in terms of the wider impacts, I mean, what do these situations mean in terms of global impacts? Well, a child will die approximately every 2 minutes currently from a water-related disease. So by the end of this talk, about 30 children will have died from a water-related disease. And 160 million children will suffer from growth and stunted growth and malnutrition due to water diseases, not due to lack of food, but due to water-related diseases. It has a major impact, as we can all appreciate, on the health of global ecosystems. It manifests itself in Ireland in, for example, rivers, or when we see beaches that have to be shut down because of wastewater discharges. In terms of the economics, it's actually one of the safest capital investments you can make, safer than almost any other capital investment you can make, and it becomes even more so for developing countries. So your return on investment is approximately 4 to 1. For example, many transport projects might be just above 1 or 2, particularly when it comes to road projects. So it's a very safe investment. In developing countries, that might rise to about 30 or 40 to 1. And it consumes about 4% of the world's electricity. And that varies widely and can go up to about 16% in the Middle East. So it's a major electricity consumer, and 4% mightn't sound like a lot, but for one single industrial sector, that is an enormous amount of electricity. In terms of the financial impacts, well, sadly, it would only take about 114 billion per year to solve the problem of improved sanitation and water facilities for everyone. So the problems are clearly not financial. There are technological problems, but also a lot of societal and political and geographic issues as well. So, 114 billion is only about a quarter of Ireland's GDP, which is a very small amount to solve what is probably the greatest challenge, maybe alongside climate change, in the world today. So with that kind of background in mind and just those higher level challenges, just move on to what is this concept of digital water, which I suppose has been brewing in the water sector for quite a long time, but is now, I think, really beginning to impact the water sector significantly. And a lot of that is driven by some of the aforementioned challenges, and some of them that I will go through in the next few minutes. So digital water is really looking at the entire water system, from sources and the environment through to collection, treatment and distribution of water, and also collection and treatment of wastewater, and the end users, and looking at how we can use data to improve all of those three and the experience under each of those three headings. And it covers a lot of different things, from the implementation of SCADA and telemetry systems to hydraulic modeling of both water distribution networks, but also of entire river catchment basements. It looks at enterprise and IT systems, more efficient procurement, more efficient workflow management and maintenance, better capital planning. And on the consumer side, things like better billing systems, improved meter data management, consumer information systems. And there's also a big push now for consumer engagement channels, so making people more aware of the water they use and how they can actually reduce their water consumption. And the International Water Association have produced a very, I suppose, detailed series of white papers on the area of digital water, which are very useful for anyone who would like to look at this further. Currently, in terms of digital water, well, across much of the world, many utilities and water supplies, supply companies are not even at the stage of even thinking about digital water. As we can see, if over half the world don't even have access to, say, sanitation, well, there's far greater problems to deal with first. But then on the other side, those utilities that maybe are more developed tend to be, I suppose, at the transactional or transitional stage of digital water. So what we mean by that is that there tends to be maybe weak or some sort of ad hoc links between different parts of organizations and different types of digital solutions. There isn't any connectivity maybe between the different parts of the organizations. And also there isn't maybe any holistic thinking between the environmental and source protection side and the water supply side, and also the relationships between the infrastructure contractors and the water utility, the utilities themselves in a digital sense. In terms of translational digital water, what we mean by that is where individual parts of a water and wastewater utility have maybe taken it upon themselves to implement advanced or some digital systems or advanced digital systems, but that is maybe not an overall utility priority, but perhaps in a certain area, someone has driven that kind of, I suppose, digital transition, but it's not ubiquitous across the organization. Really where we'd like to be is what the International Water Association have called this dynamic and fluid situation, which I think is a very good way of terming it. And you can see that on the right. And really what that means is that you have different aspects of the water utility and wastewater utilities, which all communicate with each other, and whereby data is ubiquitously available across different systems and is shared both internally, but also with external partners. And this is extremely important, such as shared with academic and research partners, with industry, with the public, and also where you have a lot of deep connections between those who protect water sources, those who actually abstract and treat water, those who collect and treat wastewater, and those who manage the areas where wastewater is discharged to. So where all of those are digitally connected. So I guess it's a pathway between the existing models and this more dynamic and fluid model that we'd like to see happen. So kind of breaking down the water sector a little bit, and after that maybe focusing on wastewater treatment, which is just one part of the water sector. I suppose from my experience, looking at how well digital water is implemented globally across different systems, I would say that water distribution and consumer interactions have maybe on a global basis the deepest level of digital adoption, followed by water treatment, which is the water obviously when you turn on your tap that you drink, etc. Then source protection, which is protecting both the outlets for wastewater, such as maybe rivers, lakes, beaches, but also the sources, including groundwater for drinking water. And unfortunately, at the bottom, I would say wastewater treatment is probably the area with the lowest level of digital adoption worldwide. Now, of course, that varies from country to country and from utility to utility, but as a broad heading. Perhaps some of the reason for that is, I suspect, is that it is also maybe the most difficult area in which to implement this digital water. And some of that is down to the complexity of what happens in wastewater treatment plants. And there's also funding issues and other issues. The case for digital water across these sectors is pretty similar across all the sectors, and I'm not going to go into these headings, but into all the details, but really you have benefits at a community level, you have operational benefits for the utility, for contractors who operate infrastructure, you have financial benefits, and very importantly, and I think this is a real driver for digital water into the future, are these long-term resilience benefits. So in terms of community benefits, well, there's clear benefits in terms of health and environmental protection. Water utilities and contractors that are more digitally aware and have adopted this digital water to a higher level are also the ones that will tend to most meet regulation when it comes to both health and environmental protection. And this is the key driving force for any utility in the water and wastewater sector. Similarly, for process excellence and optimization, that means reduced costs per unit of water and wastewater treated. And it also means limiting the number of times which, for example, you miss regulatory compliance or eliminating it altogether. A huge area now is sustainability. And you'll see this even in some of the work we are doing, which I'll present later. This is becoming a key driver for the adoption of digital water. It's driven both by the need to report carbon emissions and also by the need to reduce chemical and energy expenditure. Then leading on from that, obviously, is operational expenditure as a key benefit. And moving on to long-term resiliency, benefits include things like extended infrastructure life cycles, which I think is going to be hugely important, and climate change resilience. And climate change is likely to have, and has been said by a lot of organizations, including the International Energy Agency, the World Bank, and a lot of other international organizations, will have particular impacts on the water sector. Okay, so with that kind of broader level in mind, I'm just going to move on to the area of wastewater treatment. So maybe some of you in the talk might know and be very familiar with it, but just in case, really, wastewater treatment, as you can imagine, is the collection of wastewater, which is everything that basically you flush down the toilet or everything that comes out of your sink, your dishwasher, showers, all these types of things, industrial processes and everything, the collection of this water and treating it to a certain level such that it can be discharged into the environment safely. To do that, we need to use a lot of energy in the form mainly of electricity. We tend to use a lot of chemicals, and it tends to be technology heavy, albeit a lot of that technology has been around for the last 100 years or more and hasn't changed very much, but we have made it more efficient, and there have been technological developments obviously in that time. But funnily enough, the principal means of wastewater treatment have not really changed substantially in about 100 years. You also need a lot of infrastructure. You don't see much of this infrastructure. It's because it's below our streets and roads, and you only see it when the roads have to be taken up and dug up to repair the infrastructure. And you also need people and a lot of money as well. It's costly infrastructure to install. On the other end, what we should get is clean water, or water that can be safely discharged. In some cases, it might even be reused for irrigation. And even in some countries, it will be reused as potable water again. Particularly countries like Israel and Spain, there are some examples, and across the Middle East, you will see examples of this. You will also see examples of recovery of nutrients such as phosphorus from wastewater, production of energy from wastewater, and also production of things like compost as side benefits of wastewater treatment. In between that, then, we have the issue of data, and how does data fit into this whole process? So for the wastewater treatment sector itself, and before I go into the issue of data, just some of the key challenges that are hitting that sector will be climate change. An example of that in an Irish context will be changes in rainfall patterns will have direct impacts on how our sewers operate, because our sewers tend to be combined sewers which collect both wastewater and foul water together. If you have more or indeed less wastewater, both of those, or sorry, more or less stormwater, both of those can have negative impacts in terms of your sewer system. Regulation is only getting more stringent, and with increasingly stringent regulation comes generally an increased need to use more energy and resources. It also increases costs, as does the fact that we have both economic growth and demographic growth, which both lead to more use of water, which in turn leads to more generation of wastewater. And then there are technological challenges which vary widely across the world. And many of these technological challenges in we'll say, the countries that have more advanced wastewater treatment systems are now focusing on how we can actually see wastewater, instead of it being wastewater, as actually a resource rather than a waste, which is why throughout the slides I have the waste in inverted commas, because the industry is moving in that direction. So the type of data we can gather, we gather a lot of kind of chemical data about the wastewater, what's its composition. We gather a lot of flow data in wastewater treatment plants. How much wastewater are we treating? Where are we pumping it into the plant? We gather characteristic data about what's called the sludge. So this is basically the bacteria, the biomass that we use to break down the wastewater. We gather data such as electricity data. And we also gather other kind of data such as maybe torque, RPM, other data around the operation of mechanical equipment. So that might be for operating pumps. It might be for operating sludge treatment systems. So sludge being one of the end products of wastewater. It can be operating motors for aerators, which supply oxygen into our tanks and help us treat the wastewater, etc. So there's lots of different types of data we gather, which is gathered in lots of different ways, from using inline and automated sensors to human-heavy laboratory systems. The data itself tends, like in many engineered systems, tends to be at different time levels. So, for example, we have data which is collected on maybe a weekly or monthly basis, and that might be for regulatory reporting, purchasing data, and some operator measurements that are collected on site. Then you have daily data, which might be for larger plants, lab-based analysis, looking at the performance of the treatment plant on a daily basis. Then there's also data which is collected by inline sensors, but is only logged at a daily level. That particularly happens when it comes to flow. And we have other measurements, such as measurements that indicate the health of the sludge or the bacteria that are operating in our system. And finally, we have data that is collected in periods of seconds or minutes, and that's from inline sensors, and flow and energy meters will generally comprise that data. Many of those inline sensors will tell us, for example, what are the chemical or physical parameters of the wastewater, which give us an indication as to how well it's treated. So there's a lot of different timescales, and it's collected in a lot of different ways, and it can be tricky to merge this together into a package that will control your system, improve control of your system. And what can we do with the data? Well, I've mentioned before, we can use it for regulatory compliance. This is the key need, or the key, I suppose, outlet for data. Above all, wastewater and water utilities must meet regulatory compliance, and this trumps all other issues and protecting public health. We can use it to measure whether we're meeting climate targets or not. We can use it, for example, for infrastructure resilience. Can we use existing wastewater treatment plants to treat more wastewater while maintaining regulatory compliance? In other words, can we make them more efficient, reduce the need for upgrades, and also can we model how we can adapt existing infrastructure to changing scenarios? So in the future, if we have more dry periods and more periods of heavy rainfall, can we operate our infrastructure in a way that will adapt to those scenarios? Within processes themselves, we can use it to reduce energy consumption. I'll be giving examples of this later, chemical consumption, and also for fault detection in equipment, which becomes very important because it can help prevent discharges of wastewater, of untreated wastewater into the environment, and also equipment breakdown. So the type of tools we use, and our group would work across all three of those. My own specific expertise, albeit I have research occurring in all levels, will be in the white box area. These will be what we call deterministic equations that require physical knowledge of the system and allow us to actually model the individual processes and biological chemical processes that are happening in wastewater treatment plants. The advantage of these is that they have a lot of explanatory power, which can help us with improved system design, upgrading of systems, and also scenario modeling. They can be very useful for training, but as of yet, their use for real-time process control and simulation is not really at a commercial level, because they're computationally heavy and they take an enormous amount of engineering expertise to properly calibrate and validate these models. We then have grey box models, which are, I suppose, a combination of these white box models, which are physical models of the system, and database models. They have some use in system design. They also can be used for real-time process control. They are very useful for fault detection and diagnosis, and they can have some explanatory power. In other words, they can explain some of the reasoning behind of what is going on in processes, but that is somewhat limited. And then we have black box models, which many of you may be familiar with. These are data-heavy models, for example, that use advanced statistical methods, neural networks, genetic algorithms, various other methods to mainly operate real-time control or predictive processes. They are used for fault detection and diagnosis, but they have limited explanatory power. So these are the main tools that we leverage. And just where are we now in terms of those tools in the wastewater and water sector? Well, there has been really in the last number of years an enormous amount of publications in this area. For example, some of these would look at the use of genetic algorithms for controlling wastewater treatment plants. Others would use, prediction models for control or for predicting in real time what your discharged wastewater from the treatment plant will look like. And therefore, if you can predict that and you can predict that there will be a problem, you can maybe shut down the discharge, or you could change your treatment process such that your discharged wastewater meets compliance. There's also a lot of work on the use of wastewater treatment plants in terms of demand response. So being able to operate wastewater treatment plants in periods where there's surplus electricity, wastewater treatment plants being large electricity users, but they also have to pay for their electricity. So perhaps they can be used and operated at times during the day where there is surplus electricity, which would save them obviously a lot of money and be useful for the electricity operators. And there has been some very interesting work recently on the regulatory implications of data engineering and real-time control in the environmental, water and wastewater treatment sector. And an interesting question that I've been thinking of based on actually some of these papers recently is when is too much, the balance between too much information and not enough. So for example, many wastewater treatment plants have to report their compliance on a monthly basis in terms of their discharge. If we can monitor that second by second, should the wastewater treatment operators have to report that? And if they do, if they breach their compliance on a second or minute by minute basis, should they be appropriately sanctioned for that? Or is that just an impossible task to continuously be compliant? So there needs to be a balance, and there needs to be, thinking of how this impacts regulation as well. The unfortunate thing is there has been relatively few scaled examples to date. So, there have been a lot of papers since the 1990s where the whole issue of real-time control of wastewater treatment plants, came up. But since then, there still are not a large number of, large-scale application of real-time control mechanisms across the world. So I have some examples here where it has been demonstrated for larger wastewater treatment plants that there can be significant decreases in things like chemical usage, energy usage per unit wastewater treatment while maintaining compliance. But there are also a lot of challenges with sensors, with data. The payback for some of these systems can be over 5 years, as in this case, and that can be considered to be too long for the industry. And also there's chemical issues in the wastewater, which means the application of in real-time and inline instrumentation in that sector is quite difficult. So leading on from that, what are some of the problems that we have when it comes to data engineering in the wastewater and wastewater treatment sector? I'd say the primary one, in a way, is maybe a little disconnect between the data sector and the wastewater engineering sector. So often there's a disconnect between what they think we need and what we actually need, or it could be said the other way, that perhaps we're not communicating properly or we don't yet know exactly what we need. And I think that is one of the primary difficulties that has to be overcome. From the wastewater sector, they would say that there's a lot of packages and applications offered that can generate a lot of data, but nobody really knows what to do with all this data. And I think, this is really one of the key chasms that has to be bridged in order to really roll out this concept of digital water in the wastewater treatment sector. Other issues that we've come across in our operating of treatment plants, and that I know that from talking to industry that they see as major problems, would be things like missing data. There's an issue over the reliability of data transmission. Instrumentation fouling is a major issue. you can see examples of this. Once you put any type of measuring instrument into a wastewater treatment plant, bacteria will grow in it, and that will render the instrument very quickly to be useless. That means it has to be cleaned, which in remote treatment plants may not be possible. Data transfer can be a major issue, particularly from decentralized wastewater treatment plants. There is as yet no real generalized application framework. So a lot of the work, including a lot of our work, is done on a plant-by-plant basis, but it's hard to generalize that across the sector. Capital and maintenance costs for implementing digital water, things like reliability and complexity of the maintenance in particular of these systems. And then there are the very complex relationships between what we actually measure and what we want to know. The relationships aren't very nice. There's a lot of interfering factors in these, and we are essentially trying in some way to model a lot of biological reactions, which is difficult to do. And finally, I'd say the issue of regulation versus innovation, whereby in a sector that is very heavily regulated, does that have an impact on its ability to innovate? I'd also say that maybe we need to think a little bit more about existing tools and how we can use those most effectively, simple things like Excel or indeed our own knowledge as well. And that we need to maybe integrate those into those systems better into our wastewater treatment plants. So some of our work to maybe address in NUI Galway, I'm just going to go through some of our work just to try and show you how we're trying to address some of these challenges. And a lot of this work, in fact, all of it would have been conducted with industry or in collaboration with the Irish Water, for example. And I mean, for example, the issue over trusting and instrumentation, one of the ways we've tried to solve that is develop image-based sensors, whereby the sensor itself takes certain measurements, but it also takes an image in various ways of what it's actually trying to measure, so that even if you don't trust the data that's coming back from the sensor, you can actually look at an image of it. And in this sector, often seeing is believing. It's very easy to tell the difference between wastewater, untreated wastewater, and treated wastewater in most circumstances. We have managed to implement real-time control in very small treatment plants using that have very cheap PLCs, which has been seen as a major challenge, and we have managed to implement those and show significant energy reduction costs and time savings. Maybe an issue that still has to be overcome is when those are remotely located, the sensors we use to drive these systems do tend to get fouled and clogged. In other areas, what we've tried to look at is how we can actually reduce the amount of data that we generate and the amount of metering that we need and still effectively control a water system. In this case, we are looking at water distribution systems, but it can be effectively applied in the wastewater treatment sector. A major issue for the sector and across, and indeed a lot of engineering sectors, and we've seen this with companies where they just simply ignore their online SCADA systems, particularly any false or any alarms that comes from those systems, because they get so many false alarms. And we have visited companies where they simply switch them off and the operator just detects faults themselves by eye, for example, or just by not seeing that the process is working, so everything is okay. And this is a major issue that we're trying to address as well. And also in the area of adaptive false alarm systems, so systems that can train themselves and become, I suppose, more accurate over time, and can also adapt if the treatment plant itself needs to adapt. And these will be more targeted at things like pumps and motors and mechanical equipment in treatment plants. We're also kicking off a project with a spin-out company from NUI Galway, Vortec, which is, I suppose the reason I've shown this little graphic here is that the idea of this project is to move maybe where most wastewater treatment plants are in an Irish, and in fact in a European context, which is up here at the top. And up here at the top, what we're indicating is that they either are energy efficient but don't meet regulation, energy inefficient and meet regulation, or in a lot of cases, both. The best case scenario with current technology is somewhat energy efficient and meeting regulation. And it's, again, I'll emphasize that meeting regulation is very important. And this project is trying to take this jump to being energy efficient and meeting regulation, but do so in a way that can be applied across a lot of other treatment plants. So trying to, I suppose, formalize methodologies and generalize methodologies for this process. So I'm just going to do a little story, maybe from some of our work to date has been the development of a spin-out company from NUI Galway. So I'm going to, for a minute, for 3 slides, just put on my hat as one of the founders of this spin-out company. And this company has come out of NUI Galway as a result of both, I suppose, data engineering concepts we've been working in NUI Galway. And sorry, the slide's moving on. And apologies for that. Yeah, data engineering concepts and also technology development in NUI Galway. But one of the key things about this technology, which we've developed for the wastewater treatment sector, and I won't go into the details of it, is that the technology was developed with data in mind. In other words, it was developed so that it can actually leverage data that wastewater treatment plants generate. And with this, we're looking at different types of packages, control packages for wastewater treatment plants that will actually, I suppose, leverage their existing capacity and also take account of the fact that the wastewater treatment plants themselves may not have the capacity to be upgraded. So we try and leverage what data they have or minimize the level of upgrade that would need to occur at those treatment plants to make them efficient. One example of that, and apologies for the slide skipping forward, one example that we have recently been working on in the UK is an industrial wastewater treatment plant build where we've installed the core technology of that spin-out company, but also associated with this, we've installed, I suppose, a real-time control philosophy for this particular system, and it takes data from different parts of the plant and uses it to run and control our technology within the plant. And this is the primary energy user within this wastewater treatment plant. And since we have installed it within this wastewater treatment plant, the electricity, there has been a 30% reduction in electricity, and we have had significant savings in the need for the company themselves to produce chemicals. And in a recent report for the company that we produced, we estimated these savings as being worth the equivalent of about 93,500 kilos of carbon dioxide savings every year. I've highlighted that because actually the company themselves were much more interested in this aspect, believe it or not, than the actual monetary savings of the technology, which were still substantial, because of course they are under pressure themselves to meet their climate targets, and they're looking at ways that they can actually reduce their energy and chemical usage. And so any technology that enables a system to be optimized and run efficiently is something that industry are really looking for. Okay, so some putting back on my NUI Galway hat as well. Again, some future perspectives. Well, the market for the control and automation in the water sector is 30 billion, but this is expected to grow by 6 to maybe 12% per year, depending on the reports you use. Some of the recent work that we've seen coming out will be, Copenhagen, and it won't surprise a lot of people to know that Denmark would lead the way in this area, and their key driver now for innovation in wastewater treatment plants is sustainability. For example, Copenhagen will try and be carbon neutral by, I believe, 2030. So their entire water and wastewater sector must be carbon neutral by that stage. And also there has been a drive to link the control of, or the power that can be generated in wastewater treatment plants. So it's possible to generate energy using byproducts in the wastewater treatment sector to power other aspects of the city's utilities. And this is also an example from a Danish city as well. The key drivers for these and for the digitalization of the water sector are particularly things like energy costs, which we all know, the need for climate neutral utilities, and also things such as the regulation of emerging pollutants, things like hormones and pharmaceutical products, which are currently being regulated to a certain extent, but will be more heavily regulated in the future. The International Water Association, when they looked at the 6 key tools that will be needed to drive the water sector towards energy and climate neutrality. So I've picked out 3 of the 6 tools because the 3 of these tools will rely on data engineering. So you've process optimization, which is driven by data engineering. You've the use of online sensors and real-time regulation strategies, again, driven by data engineering. You have this word control of what nitrous oxide emissions from process tanks. The minute you see the word control, you are looking at data engineering here as well. So these are 3 of the 6 key areas that they see as being necessary for utilities' energy and climate goals will heavily require or rely on data. So just to finish up the last couple of slides, I suppose the ultimate goal really for the water sector is, and again, I've gone back to the International Water Association, but I think the recent white papers in this area have been very well developed and insightful, is to look at what they're calling a water-wise, I suppose, sector. And that's a sector that holistically and together, instead of trying to do these things separately, looks at protecting and restoring ecosystems, because the protection and restoration of ecosystems is heavily reliant on the water sector and water utilities and water infrastructure providers. Protecting and restoring water resources. So these are the resources that we abstract and use for industry, for potable water, etc. Water sensitive design. So in fact, we often design in industry and even in our own homes, we design things to be energy efficient, but we rarely design things to be water efficient. And that goes from the materials which we use in industry to the actual amount of water that we need to use in our industrial and processes. And then it's to, I suppose, look at this thing of water-wise cities and communities. So to enable communities and cities to be, I suppose, in control of their own water resources and to use them as effectively and as efficiently as possible. So you would like that, eventually you would like that cities and communities will be completely self-sufficient in terms of water resources and the resources that are needed to treat and protect their water resources. So just to finish up, I'm just giving a quote recently from the Chief Digital Officer of Veolia Water Technologies. Veolia be one of the largest infrastructure providers across transport and water and various other areas internationally, AGR. And she mentioned that her vision of water, I suppose digital water in the future, is that utilities will be connected to, and she says, smart local grids that are powered by circular loops of resources. In other words, that everything that is needed to treat and protect water systems locally will be provided locally, because we will be able to extract the necessary energy from treating wastewater to power other systems, for example, or we will be leveraging renewable energies, we will be reducing the need for chemicals, etc., etc. And she also mentions then that these grids will be so local in analytics that there will be a digital twin of every household for a utility into the future. So in other words, utilities will be able to map and visualize and model exactly what is happening at a household level in terms of water resources. And I agree with that, a lot of that to an extent, but I also worry to an extent that whether we need that or not and whether that will be effective or not. And I suppose I'm going back to a quote attributed to Albert Einstein that maybe, in conjunction with that, we should be trying to make things as simple as possible, but not any simpler. And I think that's where data engineering will be really effective in the future. And I've listed 5 headings that I personally think will become very important. One is it will help us to better value our water systems. And in a lot of other European countries, water would be far more highly valued than it is in Ireland, for example, and certainly outside of Europe, in other countries it would be. I think we need to design for data at the outset. So we need to design infrastructure such that it is capable of gathering the data we need. That needs to happen at the very outset rather than installing the equipment later on. I also believe we need to minimize the amount of data necessary for lots of reasons. A, because we have the issue over data storage and excess data storage and the impact on data centers and all that. That is one area. But also because we simply don't yet know what to do with all this data, and a lot of it is unnecessary. So I think smart systems will actually use the minimum amount of data necessary. I think we need to repair that chasm or the bridge I showed earlier between data engineers and the specialist engineers in the sector. And finally, which I think will be extremely important, and I think this is something that is going to happen particularly in developed countries and developing countries, and might give them a little head start, is I think they are starting to look at data as a means of designing systems where, in fact, data-led control is almost redundant. In other words, we are able to use data to engineer our systems such that they are able to operate almost without us taking measurements. And that will be, in a way, the ideal scenario. And so just some reference and credits for the slides, and just to acknowledge my research team and various funders, and also some of our local industrial collaborators. And we're very lucky here in Galway that we have industrial and utility collaborators that are willing to work with us on these projects. So thank you very much for your time.
Thanks very much indeed, Ona. It's a fascinating insight into the challenges, but also the possibilities that exist and the initiatives underway in the wastewater sector. Probably something that, as you said, we in this country probably take for granted and don't fully appreciate the built infrastructure and how it works and the challenges that the built infrastructure is facing now and into the future. You made a point in one of your earlier, and I'll just very quickly say, if you have any questions for Owen, please drop them in the Q&A section or in the chat, and we can pick them up there. But I just picked up a point in one of your earlier slides where you talked about innovation versus regulation, as that duality there. And as we followed your slides, there seemed to be a huge degree of innovation, but where does the regulatory piece, because of that need to comply with public health? So is the regulatory environment an aid, a barrier? How do the two interact?
Yeah, I think it's a very good question. I agree. There's a huge amount of innovation. I think what maybe hasn't happened, and can briefly refer to that, is that the innovation has not yet made it to, I suppose, a commercial stage, or has not yet been widely taken up. And part of that is because in order to demonstrate its effectiveness, you need to try it at a significantly large scale. But that is difficult to do when in a sector that is heavily regulated, because you can't just try out a technology that might fail and then leads to, water getting into a water distribution network which hasn't been treated, or wastewater discharges to a beach, which results in the beach being closed down. So in a way, regulation is a necessary barrier to innovation in this sector. If I can say that, in one way, we need to have it there, and there is no issue at all with the regulation. But I also think we need to, the academic sector, the industrial sector, and utilities perhaps need to work together to, enable scenarios whereby this regulatory barrier can be overcome. And to a certain extent, we try and do that by having maybe large-scale test beds, which we can use to test technology, which are risk-free. For example, we have a small version of that in Tune, and like Galway have, where we can try out wastewater treatment technologies at a particularly large scale, but we discharge our wastewater back to a local treatment plant, so we don't discharge it to a surface water. And I also think there needs to be maybe a communication with the regulators as well, because as I mentioned before, currently a lot of regulation happens with on a monthly basis. If we start generating more data and we start to see that maybe there are little blips in compliance, what are the regulators how are they going to react to that? If, for example, we've implemented an innovative technology that allows us to actually see how we're operating more efficiently, but does also shows that maybe we're breaching regulation a little more than we thought, what is going to happen there? And I think there needs to be a dialogue there as well, so that industry can take controlled, I call it very controlled risks, But I think it's, as I said, I do think it's a barrier, but I don't blame regulators, because their remit is quite rightly to protect the environment and public health.
I suppose that there's a transition from the academic to the industry partners to the regulatory perspective on it. But one of the benefits I would have thought with data is that not only it's pretty much a quantifiable risk, as opposed to something that would surprise or be not predicted. It's something that could be potentially predicted in terms of the data modeling, but also very quickly quantified in terms of its impact and how you would respond. So I just had another question with regard to this data agenda. It seems, again, there are a lot of initiatives primarily from the academic domain, but are there any big players, like you mentioned Veolia there, are there any big players who've basically committed to or are following a data agenda?
Yeah, for sure there are. So, some of the major component suppliers of wastewater and water technology, such as companies like Grundfos and Xylem, will be two large companies. And if you Google each of those companies, you don't even need to add the word data or whatever. Most of the most recent hits will come, will, I suppose, look at how they're pivoting towards products that are data smart for the wastewater treatment sector.
Okay.
And you will also see that a lot of their products as well are products that link with data control and data management systems. So they would be suppliers of everything from pumps, valves, electrical equipment, motorized equipment to the sector. And the infrastructure providers, so I mentioned Veolia as well as one, and even locally, I mean, I don't mind mentioning we work with Warden Burke, a company based out of Kilcolgan, we work with a lot recently. And I mean, they are committed in the long term to the use of data to optimize the control of wastewater treatment and water treatment plants. I know in Irish Water, it is a major driver for them. And in fact, you know, for them, they have had to catch up with legacy issues in terms of the data that they have and the data that they can gather. But they are quickly doing that and quickly moving on to, I suppose, becoming, moving along that data, the digital water train that I kind of mentioned earlier. So I would say I would actually maybe flip it around and say that there probably is no major player in the wastewater sector that is not actively and for the long term committed to this digitalization of the sector.
Okay, there's a question here about, so I'll just read it out, that we hear a lot about the SDGs and a high priority to tick these boxes moving forward. Is there sufficient funding made available to support this, do you think? And I just very briefly mentioned a figure of 114 billion would kind of sort this. So I think it's a very appropriate question with regard to, is there sufficient funding basically to drive us towards the SDGs?
It depends. It depends on where you are. And this is a very personal opinion. In Ireland, no. I'll be honest. I don't think we fund our water sector sufficiently. I think that's pretty well known, and there's a lot of different reasons for that. In other countries, for example, I mentioned Denmark earlier on. Sweden will be another one. Yes, there would be. In fact, the key driver of the water utility sectors in terms of their funding would be movement towards addressing the SDGs and carbon neutrality. In terms of worldwide, no, but it's not because there isn't sufficient finances there. It's because it's a choice not to spend it in this area. And, 114 billion, there are plenty of companies around the world that are worth, well, maybe not plenty, but there are a number of companies around the world that are worth far more than that. So it's simply a political and a social choice not to spend it in this area. So the answer is no, but not because there isn't sufficient money in the world to do it. There clearly is. It's because there isn't sufficient willpower in the world. And I think we can see how quickly money can be leveraged during the COVID crisis. We can see that it is very easy to leverage huge amounts of money to support economies. So there is just, I suppose, a lack of political will to across all countries around the world to actually ensure that the SDGs in relation to water are met, in my opinion.
No, I think that's a very powerful point. And it's sort of, when I saw the figure of 114, the one thing that struck me was it's not the technology, it's not the infrastructure, it's the willingness. It's the ability to commit. Listen, Owen, I'd like to thank you very much indeed for your time. We're 4 minutes to the hour, and so I think I'd like to thank you all for attending and sticking with it. It's a very interesting topic, and one which I think needs to be brought front and center in terms of, water is one of the fundamental things that we depend on, and the care and attention and the focus you brought to it has been really worthwhile. So I'd like to thank you again for your time here, and to the audience for attending. Just to remind you that Rory Monaghan is up next with his talk on hydrogen. So if you haven't registered for that, a few minutes to do that. But for now, I'd just like to bring it to a close, and with thanking Owen once again. All right, thank you and goodbye.
Thank you. Bye-bye.